This is a video for AQA Further Pure Mathematics, Matrices section 5.5, Diagonal Matrices. Well, by a diagonal matrix we simply mean a matrix which has got numbers which are non-zero on the leading diagonal, for example 1, 2, and zeros everywhere else. So for a 2 by 2 matrix there's a diagonal matrix which is 1, 0, 0, 2. For a 3 by 3 matrix we might have something like 2, 0, 0, 0, negative 1, 0, 0, 0, 3, for example. I'd now like to consider some matrices which are formed by using eigenvectors and eigenvalues. So consider the matrix M, which is given by 2, 4, 1, 5, which has got these particular eigenvectors and corresponding eigenvalues. So we're making a matrix which is V, made up of the columns from the eigenvectors. So the first column V1 and the second column V2. The inverse of that would be found by swapping the leading diagonal, changing the sign on the other diagonal, and dividing by the determinant of V. Well, the determinant of V is 1 minus negative 4, so that's 5. So we get 1/5 of 1, 4, negative 1, 4. Now I want to take that and look at what we get if we take the inverse of V multiplied by M and then V. Well, that's easy for us to write down, of course. It's 1/5, 1, 4, negative 1, 1. That's V inverse. Then I've got the matrix M, 2, 4, 1, 5. And then the matrix V, which is 1, negative 4, 1, 1. Now if we multiply these first two matrices together, so we then get 1/5. We'll see that we get 2 plus 4 is 6, and then 4 plus 20, 24, second element. Moving down to the second row, negative 2 and 1 gives negative 1, and multiplying the second row by the second column, negative 4 plus 5 is 1. Then we get 1, negative 4, 1, 1. Now if we multiply those together, you'll see that the first element, 6 plus 24, is 30. The second element in the top row is 6 multiplied by negative 4 minus 24 plus 24, which is 0. And then the second row, negative 1 plus 1 is 0. And then 4 plus 1 is 5. So we end up with a diagonal matrix which is 6, 0, 0, 1. Now if we go right back to the beginning, you'll see that this diagonal matrix has got the eigenvalues 6 and 1 on the leading diagonal. And that's going to be true in general. So that taking the vector V, which is made up of the eigenvectors in its columns, calculating the inverse of V, and then V inverse MV, we end up with a diagonal matrix D, where the elements on the leading diagonal are the corresponding eigenvalues to the eigenvectors V1 and V2. So by diagonalization of a matrix then, say that if M is an n by n matrix with n independent eigenvectors, we first of all construct V from the eigenvectors of M. And then as long as V has got an inverse, we can say that V inverse MV is diagonal. So D is equal to V inverse MV, where the leading diagonal of this matrix D will be made up of the corresponding eigenvalues of those vectors. Now the fact that D is equal to V inverse MV means that we can therefore multiply both sides by V on the left and V inverse on the right, so that we get that V, D and V inverse must be equal to M. And it's this process here of writing M as V, D, V inverse which is called diagonalization of the matrix. So it's then this process of diagonalization of a matrix that we will look at in the next video.